All right, so we're talking about the push function. Like I was saying, it's just a control bit which tells the transport layer that this information needs to be moved to the application layer as soon as possible, basically. Then the reset used to reset a connection if when there's an error or there is a timeout. The synchronize, we know these ones. I think these ones are very common. Synchronize, finish. Is this finish? Fin, because fin also means end in French. These ones, we know them. Acknowledge, synchronize, finish. Is it finish? I'm very curious. What does that fin mean? Can you someone Google that for us? What does this FIN mean? I just Google FIN in connection termination. What does that mean? Or FIN control bit. It's finish. Okay, finish. Right. Reliability and flow control. So reliability and flow control are also very integral for the protocol at TCP. We look at how it is maintained in the protocol, basically. So TCP can also help maintain the flow of packets so that devices do not become overloaded. There are many times TCP segments do not arrive at their destination or arrive out of order. And what solves that one is sequence numbers out of order. All the data must be received in the data, and these segments must be reassembled into the original order. Sequence numbers are assigned in the header of each packet to achieve this goal. Right. So basically, let me see if I can use this diagram. So in the diagram, this is our client. Let me think. This is our server. Information here you can send from the client and then order 1, 2, 3, 4, 5, 6, 7. Proper. Having taken different routes. Right. My segments is very important in understanding why it's my segments. Why tizotaura nezve multiplexing, for example. Why tizotaura nezve the transport layer being responsible for maintaining multiple conversations. Customer segment, you realize with the segment 1, you're not going to travel this path to the destination. Another segment, you're not going to travel this path to the destination. Another one, you're not going to travel this path, you're not going to shika or this one, you're not going to grow up, depending on my routes akamira say, is there congestion? Are all the links up or not? So ukaita ma-segments, it means data rinokwanisa kufamba nekwariri much faster kuenda nako. Ukasaita ma-segments, it means path yatorwa ndo inotorwa kusvika up until the end. So dai tisina ma-segments, it means tikatora path iyi data rese ndo pariri kufamba naro. So in cases yekuti link raita down, that's a problem. Wakutangidzisa kuti you retransmit everything. But with the segments, since it's in multiple paths to the destination, in a path ish, what we only resend is segment advantages of let me start with working principle of the transport layer. Here, advantage is here TCP, because you don't have to retransmit everything. You can only retransmit the lost segments. Right, going now in explaining PANAP. So Tawana data rate is ordered at this end to client. Then paranoenda ku server, 1, 2, 6 is now not ordered. Then my sequence numbers, they are used to order the data. Here we have our data reordered. How does it do that? I think we'll soon learn about my initial sequence numbers and how sequencing works basically. I think there is a slide which gets us through that. Right, TCP reliability, data loss, and retransmission. No matter how well designed your network is, data loss, hey, where were we in Africa? Right, I think we're here. No matter how well designed your network is, data loss occasionally occurs. TCP provides methods of managing these segment losses. Among these is a mechanism to retransmit segments for unacknowledged data. Right. If a segment is lost, there is a gap in my sequence numbers received. That's one. If a segment is lost, it means my sequence numbers pane gap rinenge riripo. So for example, segment rikasasvika, it basically means there is a gap to receiving end. I think this one can explain it better. Tomboti segment number 3 harisinasvika. It means apa pane gap apa. Pakaita gap like that, those no rare could we have a segment missing. Then there is a request here, retransmission, could we have a segment number 3, which is missing. It needs to be resent. How do we know could segment number 3 ndo really missing using my sequence numbers? Right, there is my acknowledgements which are sent every time a segment is received. For legacy devices, digesting a little bit, for legacy devices, this is how it was done, right? So, Tomboti, I'm sending information between PCA and PCB. From this diagram, we're going to see 3 and 4 anakusendwa. Segment 3 and 4, okay, they were lost during transmission. But mamwe ese up to 10 akasendwa. My acknowledgements mawira anoita. Acknowledgement inouya ikauya yakati acknowledgement 3. It basically means kuti 1 and 2 has been received, but kutangira pa number 3 we have not received that. What my legacy devices do, my legacy meaning, let me just say the protocol ekudhara. My devices anoshandisa the protocol ekudhara isati yarefinwa. Acknowledgement yasendwa acknowledgement 3, it basically means I've received 1 and 2. Then as they will be resent. It will resend 3, 4, 5, 6, 7, 8, 9, 10. Because pane imwe acknowledgement iri pa 11 panapa. Ese anoitwa resend. However, it leads to my duplicates. Because what we are only missing is 2 and 3. So the old way of doing things, acknowledgement. All right, excuse me. The old way of doing things, acknowledgement inosendwa ndo inoitwa paitwa retransmission. Retransmission kutangira pa segment number 3. So ese avaitwa resent. However, you see anovaita ma duplicates because anenge amboita sei ambosendwa kudhara. So retransmission, it works using my acknowledgements. However, this one was not as efficient. So we have this one, inoshandisa my selective acknowledgements. Same situation, 3 and 4, they are not there. Acknowledgement 3 rinosendwa. Also selective acknowledgement 5 and 10 rinosendwa. meaning that 5 and 10 was also received. Panozoitwa recent. What is recent is only 3 and 4. 11 and 12 are kusendwa because panapa after 10 up panosendwa acknowledgement up. 11. That's why 11 and 12 are being recent. Then acknowledgement 13 rosendwa kana pane imwe information 14 and 15 zvinova zvaita sei zvadzatera etc etc. In summary, when we talk of data loss and retransmission, TCP makes use of acknowledgements to be more effective selective acknowledgements. So acknowledgement ndo rinorodza kuti information yandareceiva so far masegments api. Acknowledgement yangu yakaira chiti 3, it means I have received probably 1 and 2. Rikaira chiti acknowledgement 3, selective acknowledgement 5, 10, it means I've received 1 and 2. I've also received 5 and 10. So typical questions you will get. Let's say 6 and 7 and 8. Ndo asina kuuya. Everything else between 1 to 10 esauya except 6, 7 and 8. Zviroti acknowledgement richasendwa kunoko for retransmission. Ringe rakati acknowledgement 6. Or that acknowledgement selective numbers 9 to 10. Meaning number 6 ichasendwa, number 7, 8 ichasendwa. 9 haisendwe because iri selective acknowledgement basically. So you'll be asked my questions so that you can identify kuti pa acknowledgement pane number ipi, then pa selective acknowledgement pane number ipi basically. That's how data loss and retransmission is dealt with TCP. Then we go to flow control, another mechanism which is offered by TCP. Flow control is the amount of data that the destination can receive and process reliably. Flow control helps maintain the reliability of TCP transmission by adjusting the rate of data flow between the source and the destination for a given session. Flow control is saying, in me as a device, I'm only capable of processing this amount of data at a given time. Then you tell the sending device that information. Sending device kana yakusenda data inoshandisa information yekuti how much is the receiving device able to take in. So send depending on that. That's how they manage at-not flow control. If there is no conversation like that one, that's where we have a case yekuti 100 megabyte port receive information from 100 gigabyte port, which is a catastrophe basically. Congestion. That is flow control at layer number 2. I think ndakambopa a brief difference between flow control at layer 4, iripo, and flow control at layer 2. Two different things you need to know as well. Right. Going to our diagram, what do we have? Flow control is done using window size. Flow control is done using window size. Let me see. Let me digest. Panapa window size here is 10,000. MSS is 1460. That is the size of the segment. Sequence number 1. All right. Mm. 460 plus 1460, 2920, 2921. Right. So let's start with the window size. The window size, this one, is information which tells the sending device, the amount of information it can process at a given time. So the window size for this one is 10,000. It's also the number which is used to determine when an acknowledgement is sent. So after 10,000 has been sent, let's say 10,000, this is 10,000 bytes for this one. After 10,000 bytes have been sent, that's when we can send an acknowledgement. Window size. It indicates the number of bytes the receiver is willing to accept at a given time. Initial window size, it's not fixed. Window size is not fixed. Initial, for example, this one, 10,000. It can change depending on the receiving device how many bytes. Kana pane congestion at one day, this value is decreased. But the initial size is negotiated during three-way handshake. Patinator synchronize, acknowledge. That establishment, that connection establishment. Ndo panosendwa information yekuti inini I can only take in 10,000 bytes at a given time. The sender sends the window size, which is basically a range of bytes the sender is allowed to send without receiving an acknowledgement. So, panapa kana 10,000, it means I can send 10,000 bytes without receiving an acknowledgement. After 10,000 bytes zapinda, I then receive an acknowledgement. The more the window size I have, it basically means the more the information I can transmit without getting an acknowledgement. The send window is initially set to the receiver's advertised window size. So panapa, let's say this is our client. Let's say this is our sender. This is our receiver. The receiver ndo inopa the window size because ndo you could receive information. So that I think that's this this statement. The receiver doesn't have to wait for the entire window to be filled before sending an acknowledgement. It can acknowledge received data incrementally. As the sender receives acknowledgements, it slides its window forward, allowing it to send more data. That's why it's called the sliding window, right? The receiver can adjust its window size based on its availability. It can reduce the size to slow down the sender. An acknowledgement is sent with reduced window size. Let's explain this information using this diagram. Initial window size here, 10,000. Then we have the maximum size segment, red, which is 1460 bytes. We'll also get to explain this, the maximum size segment. Taudzwa panapo we added 10,000. It means starting with sequence number 1, I can send 1460 bytes, which is the maximum size here segment running in the Our receiver will receive the first 1460. I can send another because I send a 10,000. Our receiver, your receiver, 1460 times 2 tapa 2920. Acknowledgement Ravarauya. You can see acknowledgement number is 2921, meaning we have received the first 2920 bytes. Tikadzoka panapa. The logic was acknowledgement rikadzoka. It shows us the information yata receiver basically. Rikadzoka acknowledgement 3, it means we've received segment 1 and 2. Panapa acknowledgement irudzoka ri 2921. It means we have received 2920 bytes so far. Sequence number 2921 tosenda imwe information maximum size redu MSA0 maximum size yesegment. It gets received acknowledgement rosendwa futi. Take note of the acknowledgement number as well. Ndo ari kushandiswa patanga tiri kutaura paloss neparetransmission. Also take note of the window iri. It's increasing. Why is it increasing? Since we want to keep size here 10,000, kana tasenda 2960, it means size redu rinouya pa 12,000. Zvichireva zvokuti size rewindow riri kuramba riri pa 10,000 because send window rapa 2920, 12,920. We have already sent 2920. Ndo pari kubuda nyaya yesliding window kana tichitaura nezvesliding window. Why? Because rinotanga riri pa 10,000. Ukasenda 1,000 iro rinobva raenda pa 11,000. Ukasenda 2 rinobva raenda pa 12,000 send window. Richingodaro, it increases depending nekuti how much information has been sent. If it does not increase, rikamba riri pa 10,000. If it does not increase, let's say window size redu riramba riri pa 10,000. Patinosenda mabytes 1460 aya, 1460 aya. Let me see, divided by 10,000. I think to also send a maximum of, let me do some calculations. 1460 times 5. 1460 times 5. 7,000 times 6. 8. 7. I think we can send approximately 6 point something. Let's say 7. Window size redu rikaramba ripa 10,000. Tikasenda 7 bytes. 7 segments, I mean, ane length here 1460. It means we will no longer be able to send anything because it's tasvika per maximum window size ready. Window size inotipa an idea yekuti how much information can we send. So ukasenda 10,000, window size ikaramba ripa 10,000, it means you can no longer send more information. So window size panongori send information rinenge riku increase by the amount of information you have sent, basically. So at this point up, it means we have sent 4,380. Window redu rinenge raslide from 10,000 to 14,308. To summarize, I think I've said a lot of things. To summarize, there is what we call the window size, which allows us to see, to flow, to manage the amount of data we are sending, basically. The sender determines the window size because in Dorno determine how much information can I take in. But no stanga send the information. My sequence numbers edu, which is usually a random number. Panapa I think I'm 1, so that is very easier to understand. The sequence number is usually a random number. Because it goes pana 1 up, my attackers, it makes it very easy for them to take this amount of information they are sending because they know that every time panatanga communication sequence number and get 1. So in real systems, sequence number is not, it doesn't start at 1 per se. It's a random number and go choose one. So for example, ndikatanga 100 panapa sequence number. It means ndikasenda 1,460 bytes kunoko. Number ish inenge apa 1,561 basically. This number minus this one ichikupa the number of bytes dzinenge dzasendwa. So sequence number is just a random number. Right. So to introduce a window size, to introduce as well how the sequence number is chosen. Then we have this send window if. Which has a concept of sliding window. The window slides depending on the information inenge yasendwa. Kana uiredo rikatanga ripa 10,000. tikasenda 4,380, it means send window redo rinoslider from 10,000 to 14,380, allowing us to continuously send more information basically. Also, acknowledgement rinokupa an idea yekuti what information has been sent so far, how many bytes. Acknowledgement iro 2921, it means 2920 bytes have been sent so far. Acknowledgement rimwe iro, it means 4380 bytes have been sent so far. It might seem a lot of information now until you get to an exam. Pongo ya diagram rakadai so iri risina manhamba aya, risina manhamba aya, these numbers aya, maybe wangopiwa sequence yekutanga iyi obva wanzi fill in kuti manumbers anenge ari apa anenge akamira sei. So you need to know, use your knowledge yako yekuti ma-sequence numbers, how do they change? Ma-acknowledgement numbers, how do they change? Window size, the initial one, after sliding, how does it change? Very important. All right, flow control. Another way of controlling the traffic per transport layer. We have the maximum segment size, MSS. Maximum segment size is the maximum amount of data that the destination can receive. A common MSS is 1460 bytes when using IPv4. A host determines the value of its MSS by subtracting the TCP headers from the Ethernet maximum transmission unit. 1.5 minus 40, what. Right, so we have the MSS, which specifies, I'm talking way too fast. Right. We have the MSS, which specifies the largest amount of data in bytes that a device can receive. And we'll see this value is dependent on the MTU. We have what we call the maximum transmission unit. Patakaita layer 2, I think we talked about the maximum transmission unit. For Ethernet, you realize, let me do this. Right, for Ethernet, you realize the MTU is 1.5 bytes. The minimum number of bytes you can have, Ethernet, I think it should be 64 bytes. Then the maximum 1518. Information for Ethernet. An Ethernet frame. So an Ethernet frame can have a minimum size, 64 bytes. It can have a maximum size, 1518 bytes. Tikaisa Ethernet frame up and my fuse arrow, you see the sum of all the fields will give you my values that now up 1.5 bytes. Tikaisa Ethernet frame, go and check as well. Because Ethernet frame, all the bytes, my fuse aripo, ana source, MAC address, destination MAC address. If you add all of them, Nana FCS, what, need the payload. The payload, it should add up to this value. The payload, the payload, Canary Ethernet. It all depends on the technology Shandisa. Ethernet being the most used technology by layer 2. Do you know Shandisa as a reference? The most used technology, the most common is Ethernet. So as long as you Shandisa Ethernet, the payload yago, it is supposed to be 1460 bytes. The data itself. The data is addressed from a header at each every layer, 1460. You realize if we add if we add, so from the payload, let me do this instead. It's too big. Right, let's have layer 2 header panel. Let's have layer 3 header. Let's have layer 4 header panel. Then let's have our data. Then let's have our error check. This is for layer 2 as well. Right. Indo information here, yes, including our data, including our layer 4 protocol. Let's say we're using TCP, including our layer 3 headers. Panapa TCP, it means Panama source port, Panama destination port, Panama sequence numbers, Panama acknowledgement, header information. Then per layer 3, do Panama source IP, destination IP, and all the header information in repo. Panapa ma source mark. Then in layer 2 FCS. That's all the information you don't want to transmit at a given time. Data iri payload iri. As long as we are using Ethernet, I repeat, as long as we are using Ethernet, 1460 bytes, the maximum size segment here, 1460 bytes. FCS, if you go and check, even if you Google, you see it FCS is 4 bytes. Layer 4, my headers, upper layer 4, you see 120 bytes. Can I read TCP? Can I read UDP? I think it should have 8. Layer 3, rene 20 as well. Then layer 2, header arrow, rene 14 bytes. If you add, right now, so Ethernet frame, because irindora Ethernet frame here basically, because rene data, rene layer 4, rene layer 3, rene layer 2, irindora frame. If you add everything is 14 plus 20 plus 20 plus 1460 plus 4. Those no power 1518. Let me see. 14 plus 40. 14 plus 40 plus 1460 plus 4. 518. Those no power size. Ye Ethernet frame. The minimum should be 64 bytes. Maximum should be 146 bytes. Maximum measure it is a sum of layer 2 header, layer 3 header, layer 4 header, our payload, and our FCS. Now, Chino's MTU, maximum transmission unit, Chino determine at layer 3. Chino tangle up. It runs MTU. Most of the Jokera got MTU. Could be layer 2 and layer 3. Take define at HTC in the Runo Shande maximum transmission unit. Even though MTU is 1.5 bytes. Satellite head and trail information by Ethernet. Even though it's MTU. So you realize with the maximum size of Ethernet, 1518, it is determined by the MTU 1.5, with the MTU determined as well by the MSS, which is the maximum segment size, 140, 1460 bytes. So depending on the type of technology you use for layer 2, especially, yakaita say, it will determine the size of MSS here. Kana technology you use in a less MTU than 1.5, it means size ye MSS yako inofanira kuita sei kudecrease. Ndokwainotangira kudecrease iko. Kana yakawanda, it also means MSS size yako inoita sei inowanda so, because size frame is very important. Frame rikakurisa, it becomes very difficult to handle. I already mentioned in terms of bandwidth as well as in terms of error check. So panapa, that is everything that is being explained. That's where the 1460 bytes come from. 1460 bytes is the maximum size we can have for a segment, the maximum size of data that we can send in a segment. Then everything else, I think we've explained. My numbers we've explained these ones. Everything else follows. Typical exam questions. You'll be asked size. What is the maximum size Ethernet? You know where? 1518 bytes. Now you know to 1518 bytes zacho dzinobva kupi. Some emaheaders ese nematrailers ese kubva kumusoro uko kusvika wasvika pachipa layer number 2. You'll be asked about the MTU re-Ethernet. MTU re-Ethernet rinodeterminwa at layer 3 usati waisa the frame the trailer layer 2, which is 1.5 bytes. MTU is also determined by the maximum segment size. Maximum segment size, kana riri Ethernet rine 1.5, then kunoku rinenge rine 1.460, which is the MSS. My numbers are, you will see them in my exams. Why? Congestion avoidance. Oh. When congestion occurs on a network, it results in packets being discarded by the overload router. To avoid and control congestion, TCP employs several congestion handlings, timers, and algorithms. Now we look at how TCP manages congestion. How do you know if we are having congestion on the network? I am not getting the acknowledgements I expect from PCB, so I will reduce the number of bytes I send before getting an acknowledgement. If the sender does not receive my acknowledgements at the required intervals, that means information has kusvika on the other end. Those know congestion. So if you are not getting my acknowledgements, it means you have a problem. One of the reactions kana paitika an issue you are not getting my acknowledgements, those know congestion, those know you need to reduce speed, basically traffic. You always send, reduce the amount of traffic per unit time you are sending to the other device. I think maybe 5 minutes can finish this. Let me see. 1, 2, 3, 4. Right. Time I'm going to get paid up. One more extra session, probably less than 10 minutes. Definitely less than 10 minutes. Let's have one more.